We're going to have a basic introduction to instrumentation. And the first thing is why, I mentioned before, analog signals are commonly transmitted by 4 to 20 milliamp signals. In other words, ranging between 4 milliamp and 20 milliamp. Why do we use that instead of voltage? Well, pretend that we were transmitting a signal. And instead of a power supply, you had a pump that was pumping out a line and coming back, and we could control the pressure by throttling a valve, and we got 20 psi on the gauge, and that's equivalent to something. And okay, fine, and at the end of a long line, we find that friction has dropped that by 8 pounds down to 12 psi. So we look at the thing and say, oh, well, that's 12 psi is equivalent to da-da-da-da-da, process, whatever. No, because you're not seeing what the value was at the beginning because of line losses, okay? And a way around that would be, instead of measuring pressure, measure flow. And if I've got a little flow meter and the signal I want to transmit is 20 gallon per minute, we've controlled it with a valve. Unless there's a leak in the line or whatever, the flow at the end of the line is still going to be 20 gallon per minute. Okay, yes, there's maybe an 8 psi friction loss, but that doesn't affect the flow rate. That is why, conversely speaking, let's take a look at this. Let's pretend we were dealing with power, electricity. We want to convey a signal. And let's say we've got as you can see, we've got a power supply, and it's at 24 volt DC, and we've got a transmitter, you can see with the blue circle on it and connections. We've got a probably pressure transmitter, that is sending a signal value, and it's throttling that. Well, if you read 24 volts right by it, you say, well, that's its full output. You're going to find out at the end of this long line, it's reading 16 volts. So it's going to say, oh no, it's the controller has brought it down, or the transmitting signal has gone down quite a bit, when in actual fact it hasn't. So what we do is, instead of measuring voltage, we measure current, and the transmitter will control that 4 to 20. Let's say it's a high, whatever the signal is, it's high. The transmitter wants it to be 20 milliamps, so you got 20 milliamp there. At the end of it, even though you got a lot of resistance and dropped 8 volt, you're still going to have 20 milliamp at the other end. Now, why start at 4 instead of 0? That's because if there's a break in the line, or the current transmitter has failed, you can fire it as an alarm. Now, because there's a minimum of 4 milliamp flowing at 24 volt being the common voltage signal, there actually is a little bit of power in that line all the time. And if you've got a device that can operate at less than 4 milliamp at 24 volt DC, then it can be what they call loop powered. I'm not a big fan of loop powered devices. Avoid them if you can. Have them externally powered, not powered by the loop. Now, because the maximum output of current is only 20 milliamp, which ain't much, total loop resistance can be relatively high. For Ohm's law, and if we're operating at 24 volt DC, and I is 0.2 of an amp, which is 20 milliamp, resistance can be as high as 1200 ohms. However, transmitters often are limited to lower power values, say 600 ohm. So we must allow for PLC input and indicate to another 250 ohm. We end up with about 350 ohms of loop resistance allowable. Okay? Now, however, we can still have fairly long lines. For example, if we assume we're going to lose 350 ohms, if you're a 22 gauge wire, the total loop, in other words, from the beginning to the end and back again, can be as much as 18,421 feet. If you figure the fact that how far away can where you're reading or want the signal to go, in fact, because it is a loop, you just divide that by 2. But you can see the values as the wire gets bigger, 20 gauge, 18. By the time you get to 16 gauge, with that 350 ohm max resistance, you can have a total loop length of 73,096, call it 74,000 feet. Divide that by 2 and you're up to 37,000 feet, which is quite a healthy distance. Now, at one time, you could get dedicated telephone pairs from the phone company, but this option, because they've played games with them and are using, essentially is no longer available. They even got rid of grandfathering. You simply can't get it. Now let's talk about some of the devices that we're dealing with. Pressure transmitters will have an instrument range which defines the capability of the unit. Say 0 to 500 psi. It'll then be calibrated for the desired span, say 0 to 300. In other words, we don't need or want the full thing. So we'll calibrate it where 4 to 20 is 0 to 300 psi. So basically what you're saying is the pressure is 0, it'll be 4 milliamp, and at 300 psi, 20 milliamp. In most cases, the lower range limit is 0 and the upper range limit is desired is 300 psi. Okay, so you can see on the bottom, these are these expressions. When they talk about span, that's from the lowest to the highest, and that's taking you from 4 milliamp to 20 milliamp, okay? And a span of 300 psi, 0 to 300. The maximum range of the device is actually 0 to 500, but we're not using it, okay? We don't want it. However, in some cases, that lower range limit can actually be moved a bit. For example, let's say we're dealing with an elevated reservoir and we want the thing to transmit 4 milliamp at 50 psi. Okay, transmitter will pass at 50 psi, where we're starting from, and ending up at 300 psi. So you can see we've raised that up. So at 50 psi, we're at 4 milliamp, bottom end of the red line, and at 300 psi, we're at the top. So our span has changed from 50 to 300, but we still, the maximum range of the instrument was 0 to 500, okay? Now, besides any pressure is like voltage. It always needs two locations. Essentially, all pressure transmitters are differential. It's just the more common gauge pressure transmitter. The reference is to ambient atmospheric pressure. It's like you're reading a pressure gauge. Now, if you have a housing that could accept two different inputs, then you can have a differential pressure transmitter. That'll be the difference between the two. And you can see the instrument. If you've got a single connection, it will handle a single gauge pressure only. But if you want the differential between two pressures, then you can use a differential input device, which has two. Obviously, if one of those inputs is 0 atmosphere pressure, then it will play like a single pressure device. It costs more money just for the sheer fun of it. Now, when it comes to choosing pressure transmitters, there's sort of three different ranges to play with, three different types to play with. At the bottom end are OEM style, which are used in somebody's building a control cabinet for something, but it's OEM and it's not, doesn't need to be very fancy. Those are cheap as dirt, but there ain't much you can do with them. At the high end are process transmitters that are full featured digital communication and can offer high accuracy but at high cost. Usually, even the gauge pressure transmitter, the giveaway is that double input. You can see the pressure device. You see where they've got three in a row connection ports at the bottom of this device with the blue ring on it. On the left-hand side and the right, in between is the part that is actually sensing pressure. And if you leave one to atmosphere, it becomes just a single pressure that it's dealing with. Those are nice, but they are god expensive. In between, most people offer what I call a just right transmitter. Has all the features you'd want with Municipal, along with quite acceptable accuracy. Typically, engaged versions have a single 15 millimeter NPT connection and display in desired units that you want. So they're not as cheap as the OEM style, but they're real world and do have a lot of useful features. You'll hear the expression heart, H-A-R-T, have a heart, where there's a reasonable possibility of having to change the lower range limit and or upper range limit of a transmitter in the future. Smart transmitters are available that can be field recalibrated. The most common approach is to utilize the HART, Highway Addressable Remote Transducer Communication Protocol. And how that works is, let's say here's your, it doesn't have to be a loop powered transmitter. This one has been labeled such, but it can be externally powered. But basically you've got your 4 to 20 current loop. You've got a resistance, PLC input, whatever, about 250, not 350. We're lucky the rest can be current, or be the loop itself, and 24-volt DC. And that transmitter will be programmed with a lower and upper limit and ranges and whatever. If you want to change those settings and the unit is HART compatible, you get a HART modem, which basically ties onto the loop, the current loop, and ties into a computer, and you can reprogram that transmitter to do what you want it to do. Level indication. Water height can easily be converted to pressure, given that a meter of water is 9.8 kp and a foot of water is 0.433 psi. If we have a reservoir that is 25 meters high and we tap into the drain connection, why you do that? You don't want to use an outlet or inlet, because they will move as this water is taken out of it and as water goes into it. Where the drain connection, short of draining, should be nice and steady, but it is a fairly large chunk of pipe that you're getting your values from. So that is a good place, and very often has a vault around it. That is a good place to have your pressure transmitter, which in this case is a level transmitter, effectively. Okay? If we have a reservoir that's 25 meter high and the drain connection, okay, 25 meters at the drain connection, and we have a unit that's calibrated for 30, this will provide a 4 to 20 milliamp signal of the level above. Transmitter should be installed in the center of that drain pipe so that air at the top or debris at the bottom won't be seen by the pressure / level transmitter, okay? Now, should that level device, level transmitter, be located well below the tank drain pipe, like a valve chamber, the lower range limit can be recalibrated to have 0 not be at the pressure transmitter, but 0 to be, in this case, 30 meters, okay, which is the elevation of the drain connection. Okay, so it'll then read from 0 to 30. 0 being that center line of the drain connection, and upper range limit, say 60 meters, gone from 30 to 60 was a 30-meter span. Okay, that's how you would set it up if the level transmitter is quite a bit lower than what the drain connection is. Now, for pressure transmitters, one of the things you can have a problem with is dirt in the water, particularly silt. And however, you do have to consider that you're going to get large pressure surges in the line. And those pressure surges can be rough on a gauge or pressure transmitter. And of course, you're seeing spikes that you really don't want to see. So you put in a snubber, and because, as I was mentioning, silt in the water is a problem, you want something that will stay reasonably clean. And I remember years ago, a municipality, an old workman said, the only snubber that really works is the Ray. That's the name of the company. I would, from years of experience, I would agree with him. And it's a piston and rod type. And what happens is, if you look at the cutout here, inside the unit, there's a piston and with a rod going down. It's the bottom at the connection is where silt will be. Every time the pressure goes from up or down, that piston will move, and in doing so, at the tail end, the bottom of the rod will poke away any debris that's caught. And it's the distance between the rod and the outside the housing it's in that serves as the snubber. Okay, so you can adjust depending on the fluid involved. But the basic one that I would recommend is the Ray model 060B, which is a half-inch connection and does work. And a way of putting this stuff together is as I've shown here. You've got a tap with an isolating cock, then you've got the snubber, and then you've got a cross. And on the right of the cross, you're going to an altitude gauge so you can see what the level is off the gauge. On the left, you've got a needle valve. We'll get to that in a minute. And then at the top, you've got the pressure transmitter. Okay, and I've described all this stuff here. Where that combination is nice is because you can simulate a situation. Same as we were talking with altitude valves before. You can, if you're at a high pressure, you can shut the isolating cock with the needle valve, bleed it down, look at the altitude gauge and see how it's going down and see what the pressure transmitter is doing, okay? And then when you're low and you want to go high, then you shut off the needle valve, open the isolating cock of air, and you can raise the pressure back up. Now, when you're measuring pressure with wastewater, you obviously are dealing with debris that would clog a snubber and certainly a bare gauge connection. There's a number of different ways of doing it with diaphragms or whatever. This kind of device here, which basically fits between pump flanges or pipe flanges, through bolted wafer style annular spool type pressure sensor assembly. The classic name is Red Valve has them. There's others. When that's done, it's done as a calibrated. The unit should be filled with a fluid, basically silicon oil, which, so when the pressure builds up, you see inside the ring of that thing, you see a bit of black. That's where the pressure is being seen, and that pressure is being transmitted through by liquid to the gauge at the top. That has to be done by an instrumentation shop, a certified instrumentation. The contractor's cousin is probably not the best one unless he happens to be a certified shop. Okay. If you want to measure pressure in a well, you can get submersible pressure transmitters. And the classic way of doing it in a well is to have a 1-inch Schedule 40 PVC pipe to which the transmitter will easily fit, and you have that pipe going down to the well to just above the pump itself, and the bottom of this should say terminate just above the pump with a cap serving as the transmitter end cap. In other words, drill a hole in the bottom of it so water can get into it, you've got a cap at the bottom which will stop the transmitter from falling clear of the pipe, and drill in a couple of 6mm vent holes so water can get inside. Now, the interesting thing with these things, again, it's always reference. And what these submersible transducers do is the cord comes up to the surface dry and will have a ventilation tube running the whole length. Okay, so that must be protected from moisture. In other words, that vent tube that you can see there, it's a little tiny thin vent tube, has to be protected from moisture, some sort of enclosure, whatever. Tell you, had a situation where they got flooded and found out that in fact they can be restored. Put it in an oven, talk to the manufacturer. It can be put in an oven, it can be dried out, and when it's dried out, it will go back to operating the way it should. Now, level transmitters. If we're not using submersible transmitters and stuff like that, which you can use in wastewater, and there's all sorts of non-contact, there's ultrasonic, da-da-da-da-da. My own personal preference has been, for non-contact, is to use audible. In other words, ultrasonic, call it what you want. And basically, the unit will power a remote transducer that gives a periodic click, and you can hear it. If you put your hand on the transducer face, you can feel it. Click, and then it'll wait a little bit, and click, away it goes. The recurring echo from the liquid surface is evaluated by the basic unit to determine the distance between the transducer face and the liquid. The algorithm used for return echo evaluation is ELF, which means A, because you're going to get a number of signals, and just to let you know how this thing works, it takes a look at ELF. A is which sound returning has the largest area. L, which sound return has the highest height, the loudest. Which sound returning came first. If all three coincide, the signal is rated as having a high confidence factor. The more they disagree, the lower the indicated confidence factor. These units are highly configurable and typically provide a self-powered 4 to 20 milliamp signal to the desired span. In other words, it serves as a power supply as well, but gives you a 4 to 20. Typical units have a range of 50 feet or so, but typically have a blanking dead zone. In other words, for the first foot, you're simply too close for them to work. The sonic beam is rated 6-degree cone angle, which it gives us minus 3 dB loss. This is for sound people, not us. We're not of sound mind or body. And objects that might return a false signal should not be within this 6-degree cone. In other words, you want it clear of the ladder. And if you can see in the little drawing there, the echo, down it goes, up it comes. And this unit's mounted at the top, and of course nothing can be within that foot range. And there's a collection of different transducers that you can get. The one we used at the time was called Miltronics, which was bought out by Siemens. They made some changes, none of which I object to, so Siemens. If necessary, a stilling weld or guide beam tube can be used to move the start of the cone beam to the end of the tube. In other words, if you do it this way, you can set it up. You've got a vent tube and a still pipe, and the echo down below is guided by, really the 6-degree starts at that bottom. Why the 45-degree? Because it doesn't give you a return that you get from a 90-degree cut. It'll see that as a bit of a thing, okay? And make sure the transducer nozzle does not make physical contact with the pipe. Okay, you got some clearance at the top. Here's another standard from Municipality, and you can see it, which allows you to go down and through a wet well platform. This is where they've got a platform in the wet well. And again, set up, it will be measuring from that point down, from where the 90 or 45-degree cut is, down. Okay, and it sort of guides the beam, the sound beam. Flow meters. There's umpteen different ways to measure flow. Open channel measurement, where you're measuring the level in a channel through a device. Propeller flow meter, ultrasonic flow meter, turbine flow meter, paddle wheel flow meter, magnetic flow meter. And there's basically the turn down ratio. In other words, what kind of range can they actually give you accurately and where you use them. Water, wastewater, any of them can be used in water, but wastewater, really open channel or ultrasonic. The others don't like particles. Okay. Table is a general view. Manufacturers will often claim other than what you see there, but I would use that table based on experience. I think is useful. Now, flow meter accuracy and repeatability. While the terms used vary somewhat in interpretation, the accuracy of a flow meter generally leads to the difference between indicated flow and actual flow. Since the accuracy of a given flow varies slightly, and even with identical size, the concept of inaccuracy is often expressed as uncertainty. This is a significant issue where custody transfer is involved. You want accuracy. In other words, if you've got a flow meter, and most of these will total by themselves, by the way, but you can total within a PLC. Basically, I want to move 30,000 gallons from this to that truck. Okay, fine. You're measuring flow, so there is where accuracy is important. Repeatability is slightly different. That comes down to the ability of a flow to provide repeatable readout reason, even given the same circumstances. Factors important where flow meters use ice to pace dosage rate, like chlorine or whatever, and repeatability is usually not significantly affected by installation configurations. appreciate in water treatment, dosage rate often determined by other factors. So repeatability, you're going to play games with the dosage rate, but you want to ensure that if I've got a certain flow rate, I'm applying the chemical as needed. So with dosing, repeatability is more important than actual accuracy. Now let's go in a little more detail of all the different types. Open channels, and there's different types of weirs that are used. Basically, these are put in a channel so you can be a venturi or whatever. They don't provide great accuracy, and they obviously can't be used in pipes, um, but they're reasonably accurate and useful in their own location, like discharges from treatment plants and stuff like that. Propellometers are intended for pipes. They're relatively simple, but only fair turn down and accuracy, tolerate a degree of debris. Would recommend open channel for any open flow measurement and prop meters for basic closed pipe measurement. Ultrasonic meters. Ultrasonic meters have the advantage that they can be externally installed on an existing pipe. In other words, you don't have to do much with the pipe, you can even strap them on. As a flow measuring device, they have a reputation of being less reliable but less costly than mag meters. But the cost of electronics and fierce mag meter competition has brought the price of mag meters down. So that's not a big deal. Now, with ultrasonic meters, there are two different ways they can be configured. One is Doppler. In other words, you can have where basically it's sending out a sound beam and bouncing off particles in the flow, and it then comes back. And you can have Doppler, where you're actually measuring the transit time of the sound between two different ways. Obviously, the Doppler has a problem if you don't have solids. Transit time is going to be more reliable, and you've got two pucks. You're basically shooting between a transmitter and sensor at a given angle. Now, you can have, that's the single path, as you show immediately to the right of it, or you can actually do a bounce and do it as a what they call a V system. Okay, V system is the bounce, it's straight transit time. V system is a bounce, or single path where you're coming in at an angle. Okay. Personally, I'm not a big fan of ultrasonic. As they say, it's the flow meter of the future and always will be. Turbine meters are an improvement over prop meters. They're more costly than prop meters, and they don't tolerate debris as well. And I'm not a big fan of either meter in general circumstances. Propeller meters, simple, low cost, and perform well if properly installed. You can get a hot tap where you can actually remove the meter without having to shut down the line completely. Disadvantage, sensitivity to installed position and a susceptibility to debris and wear. Seen them, they're good for pacing devices at times and just sort of giving you a rough idea of what is happening in terms of flow. Mag meters, to me, are the answer. They've come to dominate pipeline flow because of their broad turn down accuracy and insensitivity to most installation parameters. Realize they only work with a conductive fluid, water and wastewater being water with stuff in it, both are fully conductive. So at one time, mag meters were super expensive and unreliable, just like adjustable speed solid state drives used to be. But electronics have moved, and basically, say paddle wheel meters, we're talking about those, where low cost and tight insulation are major factors. Mag flow meters for anywhere that you want performance and reliability. I'm not a fan either of insertion mags. They've proven to be very problematic. So, honest to God, mag. Now, how do mag meters work? Remember Faraday and that? Gee, that's a common thing, isn't it? Voltage is induced in a circuit whenever relative motion exists between a conductor and a magnetic field. And the magnitude of this voltage is proportional to the rate of change of the flux. Well, we have a conductor, it's the fluid. So all we need to do is create a magnetic field, and then sense the voltage that we've created. Uh, the, the conductor fluid moving, of course, is the pipe, generates, and there's a magnetic field that we run it through, and it will induce a voltage, and we measure that voltage. And since the voltage is proportional to velocity of the conductive fluid, it's directly proportional to the flow rate through the mag tube. Based on electronic theory, there's a couple of considerations with them. They will mention about here first off, they're useless for petroleum or anything insulating. They can be used, they can run into a problem if you've got very pure water. Very pure water, believe it or not, distilled water, can be non-conductive. And that obviously is a problem. But the meters have got better and better and better, and it's not that often you get water pure enough to throw them. And sewage certainly is not a problem. The meter processor, because it's picking off voltage, must reference ground. This is done away from the generated magnetic field. And if uninsulated conductive pipe is used, it can serve as a reference ground. But inevitably, if you got, in other words, if you've got pipe that's non insulated, use it. But the proper way to do it really is to put in mag meter ground rods. And classically, sensor tubes should be provided with this is reading a spec, two 300 series stainless steel grounding rings. These are the things you can see wires are connected to the meter. Minimum 10 millimeter thick, which is about 3/8 of an inch, something like that. And minimum OD equal to the flange bolt circle minus bolt hole size complete with straps. So that you can, what we're saying here with minimum OD equal to the flange bolt circle minus bolt hole size complete with straps, that we can actually fit this thing between the flanges and have it retained. And you can see it's being mounted in here. We're assuming gaskets, if we'll get into that in their very last talk, gasketing and everything else. But there's basically how the ground ring for mag meter works. Another thing, installing them, they don't like entrained air. So you can have problems mounting them vertically because with downflow, upflow is fine, but with downflow, air can be entrained and that'll throw it. Now, they're talking here's the no's and the yes. No, because it's downflow and air can be entrained and coming down, splashing, whatever. Straight run required. No, we're too tight. We haven't got these straight runs of pipe in front. We'll get to that in a minute. Best is flowing upwards with some distance. And good is where we normally do it. Okay, an up elbow at the end to make sure, again, that air doesn't pocket. And classically, the inlet piping, if you're going to have straight lengths, inlet piping should be twice as long as the discharge piping, okay? Reduced magnetic flow meter sizing. Boy, this has shades of talking about automatic control valves. Mag meters are typically designed for a maximum flow velocity of 32 feet per second, which is about double normal pipe velocities. So you should always think about using meters that are one size smaller than the line. The one size smaller with proportional reducer increases will not only have an appreciably higher, will not have an appreciably higher head loss because the Venturi effect of the reducers down and then up will recover a lot of any losses, but it will cost less, smaller meter. Due to the higher through velocity, the one size smaller meter will be more accurate at recording low flow rates, and the reducer increaser will actually minimize the effect of elbows and valves. Many manufacturers recommend this approach, and it should be noted that most reduced line to meter sizes correspond to reduced port automatic valve line to port sizes. We talked about that, okay? Now here's what you're talking about, is taking a mag meter, a size smaller, and using a reducer on the inside and an increaser on the other side. And they recommend a maximum 8-degree angle. So if you use fittings, either cast or ductile preferred, ANSI B16-1 dimensions of reducer and increaser, then you'll be safe. Um, Welded or grooved reducers should not be considered because weld reducer increasers and Victaulic or grooved end reducer increasers are more than 8 degrees. Now, here's the combinations, and they all work fine. They would give that less than 8 degrees that you have to have. So if you've got a 3-inch line size, use a 2-inch flow meter, and at 12 feet per second in the main line, the throat velocity will be 27 feet per second, still within what they're capable of 32. And you can see the size go down. Let's pick a 20-inch line. 20-inch line, use a 16-inch meter, that's 2 sizes down. At 12 feet per second line, it's 18.8 through. And again, those higher velocities through the meter mean they can go down to lower flows accurately. Now, there generally are 2 variations of mag meter available from manufacturers. The first can be classified as suitable for process and having meter uncertainty, accuracy, within 0.5% of actual flow down to 1 meter per section. And the sensor tube inherently meets EMAC size or type C IP67 temporary submergence. The second variant, so that's sort of your general one that you're going to get. They will offer a second version that can be effectively considered a custody transfer. Meter uncertainty is from 0.5% is down to 0.3, down to 1 meter per second flow rate, and the sensor tube inherently meets EMAC type 6 or IEC IP68 prolonged submergence requirement. Say standard meters are rated 0.1% range repeatability at flow rates above 0.5 meters per second. They are good. Mag meters are really accurate. This is showing, it hasn't been downsized, probably should, but anyway, factory test rig where they're testing the pump flows using the mag meter. You can see it to the left there, kind of a silver colored. You can see the pump and the control valve here. There's a pump. I think it's a submersible. Anyway, on the left-hand side. Yeah, that's why you can't see it. Either submersible or vertical turbine. It's a factory that's all they make. And you see the loop at the top to make sure that the pipe remains full. Okay, hope you found that of value, and we'll carry on accordingly.